2026 A-Level Combined Mathematics Paper 1 Part B Question number 14 Part A. Part B of this same question will be discussed in a future video, link in the top right. Part A of this question has to do with functions, their derivatives, their second derivatives, and analyzing these derivatives in order to draw the graph of the function. The question says, let fx be equal to alpha times x minus 1 divided by x plus 1 whole thing squared plus 4 for x element of the real numbers minus the value of negative 1, where alpha is some element of the real numbers. Now given this setup, we are asked to show that f prime x, which is the derivative of the function f of x, is given by f prime x equals 4 times alpha times x minus 1 divided by x plus 1 cubed for x element of the real numbers minus the value of negative 1. After the question then says, it is given that the gradient of the tangent line to the graph of y equals fx, which is basically the derivative of fx, is equal to 8 when x is equal to 0. And with this information, we are to show that the value alpha is equal to negative 2. Now after the question then says, find the interval on which fx is increasing and the intervals on which fx is decreasing, and also find the coordinates of the turning point of the graph of y equals f of x. After the question then says, sketch the graph of y equals fx indicating the turning point and the asymptotes, and finally it says, hence state the range of f and also the smallest value of k such that the function f is 1 to 1 on the interval from k inclusive up to infinity exclusive. Now to start off with this question, let's write down the function f of x and try to find the derivative f prime x. So let's say fx equals alpha times x minus 1 divided by x plus 1 whole thing squared plus 4 for x element of the real numbers minus the single value of negative 1. Now the reason we have this value removed is because if x is equal to negative 1, then on the denominator we'll get negative 1 plus 1, which is 0, so we'd have a divide by 0. To avoid that, we remove the value of negative 1 from our domain of x. Now with this, if we consider taking the derivative here, f prime x is equal to the derivative of this whole function with respect to x. And considering the function, we have to substitute this whole thing into here. So we have this whole thing's derivative, and in here we can see the second part, which is the plus 4, can be easily found for the derivative, which can be derivative of 4 with respect to x, and the derivative of any constant with respect to x is equal to 0. So therefore, the derivative of this part of the plus 4 is 0. Now then, if we consider the other part, which is this part right here, the derivative of this can be found by using the quotient rule. If we take the alpha out as a constant, we have alpha times the derivative of this bit on the inside, which I'm going to write as x minus 1 squared divided by x plus 1 squared. Now in order to find the derivative here, what we need to do is to use the quotient rule. The quotient rule states that if you have function f which is equal to g divided by h, then the derivative, which is going to be f prime, is equal to g prime h minus h prime g divided by h squared. So for this, if we apply this condition into here and we take g of x being equal to x minus 1 whole thing squared and h of x being equal to x plus 1 whole thing squared, then we get that the derivative here is equal to alpha times this function's derivative, which is going to be x minus 1 squared derivative, which if we take the derivative is going to be equal to 2 x minus 1 times the first function, or rather the second function, which is x plus 1 whole thing squared minus the first function, which is going to be x minus 1 squared times the second function's derivative, which is going to be derivative of x plus 1 squared, which is going to be equal to 2 times x plus 1. So we can write 2 times 2 x plus 1 all divided by the denominator function squared, which is going to be equal to x plus 1 squared, or x plus 1 raised to the 4th power. Now simplifying this, we can see if we divide one of the x plus 1s on the denominator by this x plus 1 and this x plus 1, we will get alpha times 2 x minus 1 times x plus 1, because one of these will get cancelled, minus 2 times x minus 1 squared, since the x plus 1 got cancelled for one of these on the denominator. And on the denominator, if we cancel one of them, we'll be left with x plus 1 cubed. Now simplifying this down, we can see on the numerator we'll get alpha times 2 times, and then here we have the difference of squares of x squared minus 1 squared over x squared minus 1 minus this bit right here, which is 2 times x squared minus 2x plus 1, and that's divided by x plus 1 cubed. Now simplifying further, we can see on the denominator we'll have x plus 1 cubed as we have here, but on the numerator we'll have 2x cubed and minus 2x cubed cancelling, and after they cancel we'll be left with 2 times negative 1 and minus 2 times minus 2x, which is going to be plus 4x, and minus 2 times plus 1, which is another minus 2. So we'll have alpha times 4x minus 2 minus 2, so minus 4, and that's going to be divided by x plus 1 cubed, which if you factorize out the 4, we can see we get 4 times alpha times x minus 1 divided by x plus 1 cubed, and this result is exactly what they wanted us to find in the question. So with that we're done. All we have to do now is to state that this is valid for the values of x which are elements of the real numbers, except for the one specific value of x for which the original function does not exist. So here to say this is true for x element of the real numbers minus the single value of negative 1. And with that we are done with the first part of the question. Now moving on, the question then says it is given that the gradient of the tangent line to the graph of y equals fx when x equals 0 is equal to 8, and from this we have to show that alpha equals negative 2. Now what this really means, what it means for the gradient of the tangent line to the graph of y equals fx to be having a gradient of 8 when x equals 0 is that the value of the derivative f prime x at x equals 0 is equal to 8, since the gradient is equal to the value of f prime x. So according to that, if we go down, we can say according to data the value of f prime x at x equals 0, which is going to be f prime 0, is equal to 8. Now substituting, we can see we'll get 4 times alpha times x minus 1, which is 0 minus 1, divided by x plus 1 cubed, which is 0 plus 1 cubed, equal to 8. And simplifying, we can see we get 4 alpha times negative 1 divided by 1 equals 8. So we get negative 4 alpha equals 8, and dividing both sides by negative 4, we get alpha equals 8 over negative 4, which is negative 2, and therefore we get alpha equals negative 2. Now after the question then said find the interval on which fx is increasing and the intervals on which fx is decreasing. Now for this, what we have to do is to consider derivative function here and then see which ranges on which the derivative function will have a constant sign and which points on which the function may change its derivative value. Now in this case we can see x minus 1 will be 0 at one point and x plus 1 will also be 0 at one point, and therefore the sign can potentially change at those 2 points. Now when x minus 1 is equal to 0, x will be equal to 1, and when x plus 1 is equal to 0, x will be equal to minus 1, and therefore when we analyze the derivative we need to consider these values of x equals 1 and x equals minus 1 as goalposts at which point the sign of the derivative could change. So for this, what we're going to do is to draw the standard table where we mark the ranges of x with these special values of x equals 1 and x equals minus 1 as goalposts, and then consider all the values of f prime x in between those values of x. So there we are, I've drawn the table, and in this table you can see for the ranges of x, the first range we're going to have is from negative infinity until the first value of x at which something changes, which is x equals negative 1. The next range is going to be from x equals negative 1 until the next value of x at which something changes, which is x equals positive 1. And the last one is going to be from x equals positive 1 until x equals positive infinity. Now if we consider each of these ranges separately and consider the sign of f prime x, for the first one we have x in between negative infinity and negative 1. And for this we have alpha, which is a negative number here, so a negative number times x minus 1, which is going to be a negative number, divided by x plus 1 cubed, and since x is less than negative 1, this number is going to be a negative number, so we have a negative number cubed. So if we consider the signs here, we have alpha, which is a negative number, times a negative number on top, divided by a negative number cubed. So negative number cubed is still negative number. So we have a negative number divided by a negative number here, which is a positive number, and then minus a positive number is a negative number. So therefore the overall sign of f prime x is equal to negative. Next, we consider the next range of x in between negative 1 and 1. For this range going up, alpha is negative, but then we have this value right here, which is going to be a negative number since x is less than positive 1, and therefore this is negative. However, the number on the denominator here is going to be a positive number, as this number is bigger than negative 1. So due to that, we have a negative number times a negative number divided by a positive number cubed, which is going to be equal to positive number. So going down, if we write that down, we have negative value for alpha times a negative number divided by a positive number cubed, which is going to be equal to a positive number. Now for the final range, we have x's bigger than 1, and due to that, if we consider the values here, we have alpha being a negative number, we have 1 or something bigger than 1 minus 1, which is going to be a positive number, divided by a positive number plus 1, which is going to be a positive number. So this is positive, and only the alpha is negative. So therefore going down, we have a negative value of alpha times a positive number divided by positive number cubed, which is going to be equal to negative number. So we can see f prime x is going to be negative in this range, and will only be positive in this range. Now they actually hinted at this by the fact that they said find the interval as in singular on which fx is increasing, and the intervals as in plural on which fx is decreasing. So here we can see we have one interval on which is increasing and two intervals on which is decreasing. So completing the graph, we can see since this is negative, f prime x is negative, the graph is decreasing on this range. So we can say decreasing, and maybe just draw a line downward to indicate, or arrow downward to indicate decreasing. On this range we have positive gradient, and therefore it's increasing, so going up. And finally on the last range it is decreasing once again. So we can write for this one also decreasing and downward arrow. So this is the behavior based on the derivative of f of x by finding the sign of f prime x and finding each of the ranges on which it's increasing and decreasing. So as a final statement, we can say f prime x is positive. Actually, we'll just say directly fx is increasing. We'll say fx is increasing on the interval, the single interval of x in between negative 1 and 1. So we can say negative 1 less than x less than 1, and fx is decreasing on the intervals negative infinity up to x equals negative 1 and x equals 1 up to positive infinity. Now you could write this in the other interval format, and write it as negative 1 comma 1 like this. This means exclusive negative 1 all the way up to positive 1, and for these other two you could write them as negative infinity exclusive until negative 1 union, and then you could write 1 up to positive infinity. That's also valid, but in my case I'm just going to write them using the greater than and less than signs. So these are the intervals that are relevant for this part of the question, and with that we are done with this question. Now moving on to the next part of the question. Next part says also find the coordinates of the turning point of the graph of y equals fx. Now for that, what I have to do is to equate the derivative to 0. So we can say turning points occur when f prime x equals 0, and with that we can equate f prime x, which is going to be alpha, or rather 4 alpha times x minus 1 divided by x plus 1 to the power of 3 equals 0. And simplifying this, we can see if we divide this or multiply this whole thing on both sides, since it's not equal to 0, that's no problem, and doing so we get 4 alpha times x minus 1 equals 0, and from that we get the value of x minus 1 equals 0, i.e. x equals 1, and we get that because alpha is not equal to 0. So we get x equals 1. So therefore the turning point occurs at x equals 1. Now for the y coordinate, we can do y equals f of 1, and doing so we get alpha times x minus 1, which is going to be 1 minus 1 divided by x plus 1, which is going to be 1 plus 1 whole thing squared plus 4, since that was the original graph of f of x. So according to that, we get alpha times 1 minus 1, which is 0, divided by 1 plus 1, which is 2, which is going to be 0 anyway. So this whole thing is 0 plus 4, and therefore the y value here is 4. So according to that, we can say therefore the turning point of y equals fx is at the coordinates of x equals 1 and y equals 4, and therefore it's the coordinates of 1, 4. So with that, we are also done with that part of the question, and now what we will do is to sketch the graph of y equals fx, indicating the turning point and the asymptotes, and hence state the range of f and the smallest value of k, such that f is a one-to-one function on the interval of k inclusive up to infinity. Now for this, before we actually sketch the graph, we need to find the asymptote, since we didn't actually do that. So for the asymptote, what we need to do is to find the limit as x approaches plus or minus infinity of f of x, and also find the limits of x approaches a certain value. And the values here that we have to take a look at are the values that are going to be the denominator of the function f of x. So in this case, we can see on the denominator we have x plus 1, and therefore we need to find the limits on which x plus 1 approaches 0. So therefore we need to find the limits on which x approaches negative 1. So therefore I need to also apply the limit as x approaches the value of negative 1 from the left hand side, and also the limit as x approaches negative 1 from the right hand side of f of x. Now the first limit here, the limit as x approaches infinity, is going to give me the horizontal asymptote. On the other hand, these two limits here are going to give me information on the single vertical asymptote at the point x equals negative 1. Now considering the first limit, we can see as we take x approaches infinity on this limit right here, this function right here, we're going to have negative 2 times x minus 1 divided by x plus 1 whole thing squared plus 4. Now to evaluate that limit, I need to substitute in the value of f of x, and then do the trick where I divide the top and the bottom of our function by x until we get something to cancel out. So here I'm going to apply the limit as x approaches plus or minus infinity of the function f of x, which is negative 2 times x minus 1 divided by x plus 1 squared plus 4. And for this, I'm going to apply this by dividing the numerator and denominator of this rational function right here by x. So doing so, we can see we'll get the limit as x approaches plus or minus infinity of, and on the inside we get negative 2 times, and if we divide the top and the bottom by x, we get 1 minus 1 over x divided by 1 plus 1 over x squared plus 4. And now applying the limit, we can see this will become 0 when x approaches plus or minus infinity, and this will become 0 when x approaches plus or minus infinity, and therefore we have minus 2 times 1 minus 0 divided by 1 plus 0 squared plus 4. And simplifying, we can see this becomes minus 2 times 1 plus 4, which is going to be minus 2 plus 4, which is going to be equal to 2. And hence the limit as x approaches plus or minus infinity, and thus the horizontal asymptote, is going to be at x, or rather y, equals 2. At the y value 2, we're going to have on the left hand side and right hand side our function approaching the value of x, or rather y, equals 2. Now after that, we consider the other two limits. These two limits will give us information on the vertical asymptote at x equals negative 1. So if we consider the first limit, which is as we approach x equals negative 1 from the left hand side, we have negative 1, or rather limit as x approaches negative 1 on the left hand side of negative 2 times x minus 1 divided by x plus 1 squared plus 4. Now considering this, we can see we have this value divided by this value, and when we substitute -1, we can see as we approach -1 from the left hand side, this number is going to be some negative number. However, this number is going to be some positive number, or rather negative number, as we approach x equals -1 from the left hand side, since this value of x is going to be a negative number that is bigger in the negative direction than -1. So therefore we have -2 times a negative number divided by a negative number squared plus 4. Now as this value approaches 0, we can see we're going to have this value squared, which is a positive number, times -2, which is going to be a negative number plus 4. So as this value approaches 0, we're going to have a bigger and bigger positive number times -2, which is going to be a really big negative number plus 4, and therefore in the actual limit we are going to have negative infinity here plus 4. And the reason we have negative infinity here is because on the inside we get positive infinity times -2, and therefore we get negative infinity plus 4, which the plus 4 becomes irrelevant, and therefore the final answer for this limit is negative infinity. Now similarly, if we consider the other limit here, for this limit we have the limit as x approaches -1 from the positive side of -2 times x minus 1 divided by x plus 1 squared plus 4. And in this, again if we consider the values on the inside, x minus 1 is going to be a negative number, so we have negative number divided by x plus 1, which in this case is a positive number, since the value of x is some value that is greater than -1. So we have negative number divided by positive number squared times -2 plus 4. Now considering that, even though we have negative number divided by positive number, which is a negative number here, when it gets squared, it's going to be a positive number. So this is a positive number times -2, which is altogether going to be a negative number plus 4. And as this denominator approaches 0, as x approaches -1, we're going to have a really small number of the denominator, which creates a really large positive number here, which will end up creating a real large negative number over here, and therefore in the limit we will get a real large negative number, which is negative infinity plus 4 as the value of the limit. So here we can see the plus 4 becomes irrelevant, and therefore the final answer here is going to be negative infinity as well. So on the left hand side and right hand side, both of these limits are equal to negative infinity. Now what this means is that at the point x equals -1, from the left hand side our graph is going to approach negative infinity like this, and on the right hand side also it is going to come from negative infinity like this. So the asymptote will look like this. Now usually in these questions, in addition to this stuff, there is one more thing that they will either give us or ask us to find, and that is the second derivative. Usually in these questions they'll either directly give the second derivative or will guide you to find the second derivative. In this case, however, in this question they haven't done that. So therefore, in order to find information about the concavity of the graph, we will need to find the second derivative ourselves. So therefore what I'm going to do is to take the first derivative, substitute in alpha equals -2, in which case we get 4 times -2 or -8 times x minus 1 divided by x plus 1 cubed, and then apply the derivative rules in order to find the second derivative f double prime x. So going down we can write fx equals, or rather f prime x equals -8 times x minus 1 divided by x plus 1 cubed, and then we can apply the derivative rules to find f double prime x. So f double prime x is going to be equal to the derivative of this function f prime x with respect to x, which is going to be equal to -8 times the derivative of x minus 1 divided by x plus 1 cubed. Now for this we have to apply the derivative rule, which states that the derivative here is going to be equal to the first function's derivative, which is going to be equal to 1, times the second function, which is x plus 1 cubed, minus the first function, which is x minus 1, times the second function's derivative, which in this is going to be equal to 3x plus 1 squared, all divided by the second function, which is x plus 1 cubed, whole thing squared. Now simplifying, we can see this is going to give us x plus 1 to the power of 6, and on the numerator we have x plus 1 squared here and x plus 1 cubed here. So therefore out of that 6 we could cancel 2 of them to turn this into x plus 1 and turn this into x minus 1 times 3 times -1. So doing so we can see this will simplify down into the expression f double prime x equals negative 8 multiplied by x plus 1 minus 3x minus 1 divided by x plus 1 to the power of 4. And simplifying a little bit further, we can see this will give us minus 8 times, and if we simplify, we have minus 3x, which is going to be minus 2x with this one if you cancel, and then 1 plus 3, which is going to be plus 4. So we have 8 times 4 minus 2x divided by x plus 1 raised to the power of 4. Now considering that if we take a look at the inflection point, we can see the inflection point is going to occur when f double prime x equals 0. So we can say inflection point occurs when f double prime x equals 0, and therefore we get the equation a minus 8 times 4 minus 2x, which I'm just realizing you can factor out a 2 here to get minus 16 2 minus x divided by x plus 1 to the power 4 equals 0. And substituting and rearranging, we can see if we take this to the other side and multiply, we can remove it, getting us minus 16 times 2 minus x equals 0, and therefore 2 minus x equals 0 and x equals 2. So therefore the inflection point occurs at x equals 2. Now substituting in x equals 2, we can see f of x equals 2, which is going to be y equals f of 2 is going to be equal to minus 2 times 2 minus 1 divided by 2 plus 1 squared. So we can write 2 minus 1 divided by 2 plus 1 squared, which is going to be equal to minus 2 times or plus 4, there's another plus 4 in the end, minus 2 times 1 divided by 3 squared or 1 over 9, so that's going to be minus 2 over 9 plus 4, which is going to be equal to, this is going to be 36 minus 2, 34 over 9. So therefore the third inflection point is going to be given by 2, 34 over 9. Now in addition to that, usually in these questions we'd also draw a table of f double prime x as we change x and find the different values at which it changes its value. So for that, what I'm going to do is to consider this function, and we can see this will become 0 when x equals 2 and the denominator will become 0 when x equals minus 1. So therefore in terms of ranges, we do have the ranges that are in between positive 2 and negative 1. So drawing this graph, we can see we get the following table. Now if we fill in the ranges of x here, the first range we get is negative infinity until x equals negative 1. The next range we get is from negative 1 until x equals 2, and the last range we get is from x equals 2 until positive infinity. So considering each of these ranges, if you take a look at f double prime x, for the first range, which is in between negative 1 and negative infinity, we get negative number times this bit right here, which is a positive number, divided by x plus 1 to the power of 4, where x is something less than negative 1, and therefore we get a negative number here to the power of 4. So we have negative number, positive number, and negative number to the power of 4. So substituting in, we can see for the sign of f double prime x, we have a negative number of negative 8, positive number on top, divided by a negative number to the power of 4. And negative number to the power of 4 is going to be a positive number. So therefore we have negative number times positive number divided by positive number, which is going to be a negative number. Now next, if we consider the next range of negative 1 up to plus 2, in that range we have negative number of negative 8 times this bit right here, which is a positive number, divided by this bit right here, which is now going to be a positive number. So we have negative number, positive number, divided by a positive number raised to the power of 4. Now considering that, we can see we have negative number times positive number on top, divided by positive number to the power of 4, which is still a positive number, which is going to give us negative, positive, positive, which is a negative number. So here also, in this range also, we have a negative value. Now finally, if we consider the last range, in this range of 2 to infinity, the first value on the outside here is negative 8, and then on the inside, since this number is bigger than 2 now, we have a number bigger than 4 as minus 2x, and therefore we'll get a negative number here. So we have negative number times a negative number divided by a positive number raised to the power of 4, and therefore we get negative times negative divided by positive number to the power of 4, which is going to be a positive number. So considering that in these two ranges our graph is going to be concave in the downward direction, but for the last range it is concave in the upward direction. So according to that we can say here we have concave downwards, and if we want we can draw a little thing to indicate that, and here we have also concave downwards, but at the very end our graph suddenly becomes concave upwards like this. Now with that we finally have enough information to draw the graph accurately. So let's get drawing the graph. So as you can see here, before we start drawing the graph, I have already marked some important points on the x-axis and the y-axis that we are going to need in order to draw a graph. You can see I have marked x equals -1, x equals 1 and x equals 2, and on the y-axis I have marked y equals 2, y equals 34/9 and y equals 4. Now before we start drawing the graph, I'm also going to mark some important points that we know are already on the graph. So going up we can see we already know that our inflection point is at the point 2, 34/9. So therefore I'm going to mark that point, which is this point right here, as the inflection point at 2, 34/9. Now similarly, we also know the point 1, 4, which is going to be our turning point of the graph. And if we consider the second derivative, we can see at that point of x equals 1, since our graph is concave downward within that range, our point is going to be a local maximum. So the point here, which is 1, 4, which is this point, is going to be a local maximum like this. So I can mark this as the turning point, and I can also say local maximum, and I can say the coordinates are 1, 4. Now in addition to that, even though I was not asked to find it, I am also going to find the y-intercept of this point or this graph. So to find the y-intercept point, I am going to substitute f of 0. So doing so we can see we get -2 times 0 minus 1 divided by 0 plus 1 to the power of 2 plus 4, which is going to be equal to -2 times this bit here, which is going to be -1 divided by 1, or -1 squared, which is going to be 1, so times 1, plus 4, which is going to be equal to -2 plus 4, or 2. And therefore 0, 2 is a point on y equals fx. So additionally, I'm also going to mark this point, even though it's not really relevant and wasn't asked, I'm going to mark it as 0, 2 right here. So that is the y-intersection point of our graph y equals fx. Now in addition to that, we need to also note that our point at x equals -1 is important because it is a vertical asymptote, and as we noted up here, it is going to -infinity on both sides. In addition to that, we also know that our graph is going to have a horizontal asymptote at y equals 2, and also from -infinity until this point of -1 and beyond until x equals 2, our graph is concave downward. Now combining all of these facts, we can say that our graph is going to look like this on the left hand side, because it is concave downward, approaching a y equals 2 on the left hand side as we go to -infinity, and approaching -infinity as we get close to -1 or x equals -1 on this side. So therefore our graph must look something like this. Now it's not perfect, but the graph will look something like that. Now after that, if we then consider past -1 and consider going from -1 up to the maximum point at x equals 1, our graph is always concave downward until that point, and it reaches a maximum at 1, 4. So due to that, our graph must go up. It must also pass through this point like so. So we can pass it like this and go up until the maximum at x equals 1, y equals 4. And after that point, until it gets to the inflection point at x equals 2, it is still concave downward. So it's still decreasing like this, still going down until it gets to this point, but then at that point it is going to suddenly change direction. So until that point is concave downward, but at that point it's going to suddenly become concave upward. And after that point, until infinity, it is going to asymptotically approach the value of y equals 2, since y equals 2 is the horizontal asymptote. So due to that, we should get a graph that looks like this and starts to curve upward like this. Actually, I'll just erase that and draw it again. It's a little bit ugly. We'll draw that again. It's concave upward on that range until positive infinity. So we can concave upward it. Maybe a little bit smoother, maybe like that, to positive infinity. So that is going to be the shape of this graph. Now here, in addition to what we've already marked, we need to also mark this horizontal asymptote here as horizontal asymptote at y equals to, and do the same on the other side, and right here, write horizontal asymptote at y equals to. And similarly, we need to mark on this side here vertical asymptote at x equals -1. So we can mark vertical asymptote at x equals -1. And after marking all of them and marking the turning point, which is the local maximum, and the inflection point here, we are done with sketching this graph. Now finally, let's move on to the last part of this question, which says, hence, state the range of f and the smallest value of k such that f is 1 to 1 on the interval from k inclusive up to infinity. So for the range, what we can do is to consider the value of y that our graph of fx can give. So the maximum value that it can give is y equals 4. It cannot give any value higher than y equals 4. However, on the negative side, it can give all the way until negative infinity. So we can say from the graph range of fx is in between negative infinity and the highest value of positive 4, which is inclusive because the actual point at 1, 4 exists. So we can say negative infinity up to 4 inclusive. Now after the question then says, find the smallest value of k such that f is 1 to 1 from k inclusive up to infinity. Now if we consider our graph, we can see for, let's say, this value of, let's say, -1, our graph is not going to be 1 to 1, as for a single value of y, there are two values of x. So therefore, let's say -1 does not work. So if we start going forward like this, we can see the first point at which our graph becomes 1 to 1 is at the value of x equals 1. Because after x equals 1, for any single x value, there is only one y value, and for any single y value, there is only one x value. So due to that, our graph becomes 1 to 1 only after the point x equals 1. So due to this, we can say the graph f, from the graph, you can also say from the graph for that one, from the graph y equals fx becomes 1 to 1 after, and we can say after x equals 1, i.e. fx is 1 to 1 on the range of 1 inclusive up to infinity, of course, exclusive. Now due to this, we can say therefore k is equal to 1. And with that, we are done with this question. Now finally, let's go up and discuss the marks awarded for this question. Now before we start, it should be noted that since the official marking scheme is not actually released yet, the marks that I'm saying here are only approximations based on previous year's marks and not the actual marks of this paper. However, they're quite decent approximations, so you should be able to get a good idea of how many marks you would have gotten. So starting off, at the start of the question, when you write down f of x and then try to find the derivative f prime x, when you apply the quotient rule to this expression right here like so, you get total of 10 marks. Now after that, when you go down, simplify, and eventually get the expression that they have in the question, like so, you get another 5 marks. Now after that, when you take the fact that when x equals 0, the derivative or the gradient of the graph, or gradient of tangent of the graph rather, is given to be equal to 8, to write this equation right here, f prime 0 equals 8, you get 5 marks. Now after that, when you simplify to get alpha equals -2, you get another 5 marks. Now after that, when you then consider the ranges of f prime x, consider the values of x that you're going to need, and for each of these ranges of x, when you find whether the sign of f prime x is positive or negative, like so, for getting each of these correct and writing decreasing, increasing, and decreasing respectively, you get 5 marks, 5 marks, and 5 marks. Now after that, when you then take a look at the turning points, as in when f prime x equals 0, and you substitute this equation, you get 5 marks for equating it to 0, and after that, when you simplify to get the final answers of x equals 1 and y equals 4, and hence the turning point at 1, 4, you get another 5 marks. Now after that, when you then consider the asymptotes and find x approaches positive and negative infinity, for getting that and getting the limit and finding that it's equal to 2, and i.e. we have a vertical asymptote at y equals 2, you get 5 marks. And similarly, when you find the two asymptotes on x equals negative 1 from the negative direction and x equals negative 1 from the positive direction, and find that they're both equal to negative infinity, so the asymptote is going to be looking like this, you get 5 marks for each of them. Now after that, when you then trying to find the second derivative, for applying the quotient rule for the second derivative again, you get another 10 marks. For applying it and get this equation, you get another 10 marks. Now after that, where you then find the actual second derivative and equate it to 0 and find the inflection point, for equating it to 0, you get another 5 marks. After that, where you then find the actual inflection point and find that it's equal to 2, 34/9, you get another 5 marks. Now after that, when you then do the second derivative analysis, for each of these columns again, for getting the sign correct and then getting the concavity correct, you get 5 marks, 5 marks, and 5 marks. Now after that in the graph, for the first section of the graph, which is this section right here, for drawing the shape correctly, these two asymptotes correctly and everything, you get 5 marks. After that, for the second section of the graph, which is from the first asymptote all the way until the turning point, which is this part, you get another 5 marks. And finally, for the last section of the graph, which is from the section after the turning point, past the inflection point until the second asymptote, you get a total of 5 marks. Now after that, for their final arguments, for showing that the graph has a range of negative infinity to 4, and also for finding the value of k equals 1, for these two combined, you will get 5 marks. So that's going to be all for this video. I hope you enjoyed. If you have any feedback or questions, post them in the comments down below. Thank you for watching, and goodbye.